Gibson here. Today we're going to continue our study of linear motion and look at how we can represent that motion with graphs. So the three types of graphs we're going to look at are position, velocity, and acceleration with respect to time. Okay, so we'll introduce what those three graphs are. And then the big ideas are that the slope of a position time graph gives us velocity. The slope of a velocity time graph gives us acceleration. And the area under a velocity time graph gives us displacement. Okay. So let's start with an example of a position time graph and understand how this gives us velocity, or how we can get velocity information here. So we have two trucks and we plotted their change in position over their change in time. And the question is, how would you compare the velocity of the two trucks? So let's do the red truck first, right? We're looking for the change in position divided by the change in time. So the change in position would be 35 meters at the end, and its position at the start was 10. So 35 minus 10, and the time change is 5 seconds, right? Our initial time was 0. So if we do the math, we would get 25 divided by 5, or 5 meters per second. Let's do the same thing for the blue truck. So its change in position, it went from 5 to 15 meters over the same 5 seconds. So we would see that its velocity is 2 meters per second. So we basically calculated slope, right? Rise over run. The rise is our change in position, and the run is our change in time. So the slope of a position time graph gives us a lot of information about the velocity. We can actually calculate it. We can say, does it have positive velocity? In other words, is it moving in the positive direction? If the slope is positive, if the slope were negative, then we would say it has negative velocity and it's moving in the opposite direction. So let's look at what the full set of graphs would look like for the case of constant velocity, right? Now, we've seen this model before with our running man, and here you can see he travels 1 meter per second at a constant speed for the full 10 meters. So how would we graph his change in position versus time? Well, we would see that it gives us a linear graph. Every second he travels another meter, right? So we get this nice straight linear graph. And the slope of this graph is 1 meter per second. That gives us the velocity. Now, how about the velocity? Well, we know it's constant, and we just said, based on the slope of the position time graph, that it's 1 meter per second. Here, let's just add a couple comments here. So our slope here of the graph, where's my pen? Here we go. Our slope was 1 meter every 1 second, right? So basically 1 meter per second. So that slope now becomes our information to graph velocity versus time. So what would that look like, right? It's just going to give us a horizontal line because it's constant, but it's not 0, it's 1 meter per second. And the next step is that the slope of the velocity gives us the acceleration. Now, what is the slope of a horizontal line? If we were to go down here to this line, right, the slope for a horizontal line is simply 0, right? So the slope would be 0 meters per second squared. That becomes, right, the value that we can graph on our acceleration versus time graph. So since it's 0, it's just going to go across the time axis here in this case, okay? So, but these are the characteristic graphs that if you look at them, you should be able to determine that this is for an object that's moving at constant velocity, right? Two ways to determine that. The velocity is a horizontal line at some fixed value. the acceleration is 0, and the position time graph will be linear. It'll have a nice straight line with a specific slope. Let's look at the case now for accelerated motion. Okay, so again, we saw this same graph when we first introduced the concept of acceleration. Now here, each second, we're going to cover more distance, right? So our graph is not going to be a straight line. It actually gives us a nice parabolic shape here. Why parabolic? Where is that? It would mean a quadratic relationship, and that's exactly what we have. Remember our motion equations, right? The distance, if we're accelerating, is equal to 1/2 at squared. So this squared here gives us a quadratic relationship. Okay, so if we see a position graph that has this nice parabolic curve to it, that tells us right away that we are going to have acceleration. Our velocity is not constant. Now, the slope of this graph, right, is going to be constantly changing, right? If we were to draw a line that's tangent and say, okay, what's our slope here? And then we move a little further up, right? Draw another line that's tangent, we're going to get a different slope. And as we get higher and higher here, our slope is going to get steeper and steeper. In other words, the velocity will be increasing as this curve gets steeper and steeper. So what would that look like? We're going to be increasing our velocity at a linear rate. So every second, we add another meter per second, and we get this linear relationship now for velocity. Now, remember the equation we had for velocity. It was a linear relationship, right? We have velocity equals acceleration times time, right? There's no squared component to it. This is basically a linear relationship, y equals mx. If we add our initial condition, that would be our y-intercept here. Right, so we see that the slope of this curve, again, is going to give us acceleration. It's not 0, but the slope is constant. It's a straight line, so we're going to have a constant acceleration value. In this case, our acceleration is 1 meter per second squared. Okay, so there's the 3 graphs for both cases, where we're traveling at a constant speed and where we're traveling with constant acceleration and changing velocity. So let's get a little practice here at applying these concepts and see if we can recognize and describe what's happening based on the velocity graph. Okay, now the choices that we'll have here would be, is it 0, constant, or changing? And then is the velocity positive or negative? Same thing for acceleration. So let's look at this first case here. We have a horizontal line for velocity. So that tells us that the velocity is not 0, but it also is not changing. So we would have constant velocity, and our graphs allow us to plot both positive and negative values. So positive, we could think of as moving in a positive direction, or traditionally we think of that to the right. Okay? And therefore, if the velocity is constant, then we know our acceleration is 0. Now let's look at the case where the velocity is increasing, right? So it's still positive. We're in the positive part of the graph, so we're moving to the right. And as we move to the right, we have increasing speed. So now in this case, right, our acceleration is not 0. We have a constant but positive acceleration. Why positive? The slope of this line is positive. Okay, let's try a couple more here. So you can just pause it and see if you could figure out how would you fill in for velocity and acceleration. Okay, let's look at the first one, right? So again, we have velocity increasing at a constant rate, right? And therefore our acceleration would be constant and positive, similar to the previous one. But now the next one, notice our velocity has a negative slope. Now, at the start of time, right, we had a high velocity, as we reach at the end of our time period, we're almost down to 0. So what's happening here? Our velocity is still in the positive direction, but we are slowing down or decreasing. And therefore, our acceleration, while constant, is negative. Let's try the last couple here. So now notice we have our velocity graph down here below the axis. So that means we have negative velocity. We're moving in an opposite direction. So you could think of that as moving from right to left. Okay. But we are increasing. So we're moving to the left with increasing speed. Okay. So I'm sorry, decreasing speed, right? We started at a high speed to the left and we're moving to 0 velocity. So the acceleration in this case is positive. Remember, acceleration will be in the opposite direction if we are decreasing in our velocity. And then the last one, we have increasing velocity, but in the negative direction. And our acceleration would be constant and also negative, meaning we're going to go faster and faster in the negative direction. All right. So which of these graphs are speeding up? Which of them are slowing down? So I'll just pause here, see if you can figure out which case we have. All right, so the first one, it's clear our velocity is going from near 0 to a greater value, so we're speeding up. The second one, we started at a high positive velocity and went to 0, so we're slowing down. The third one, we started moving in the negative direction, but at a high velocity and moving towards 0, so we're slowing down. And the last one, we started at 0, but moved to a higher velocity in the opposite direction, so we're speeding up. All right, velocity time graph, as we've already talked about, gives us the slope of that gives us acceleration. So the blue truck, right, since it's a flat line, would have 0 acceleration. The slope is 0. The red truck, right, we can see that it has increasing velocity and calculate the acceleration from that. And so our change in acceleration, we went from 0 to 3 meters per second in 6 seconds. So we would have an acceleration of 1/2 or 0.5 meters per second by calculating the slope. All right, so review here, right? The position time graph, the slope of that gives us velocity, and the slope of the velocity graph gives us acceleration. Okay, so this graph here, these set of graphs are representative of motion where we are accelerating. Now, one more concept here. What does the area under a velocity time graph tell us? Well, let's think about it. How would we calculate the area under this red line, right? It's really this area here. And we calculate the area of a rectangle by multiplying the length times the width. So the length would be 7 seconds. The width, or height in this case, would be 10 meters per second. Okay, so if we multiply those together, pay particular attention to the units. Yes, we're going to get 70 as our area, but what happens to the units? Notice the length is in seconds, the height is in meters per second. So the seconds are going to cancel out, leaving us with units of meters, which is displacement. So the area under a velocity time graph gives us displacement. So this could be very useful, again, when we're analyzing graphs for their motion. If I gave you only the velocity time graph, you could still figure out what its displacement looks like by computing the area under the curve. Let's look at one that's a little more complex here, right? We started at an initial velocity of 15 meters per second and accelerated to 35 meters per second. So how would we calculate the area? Well, we break it up into 2 sections. We have the rectangle, similar to what we did in the previous one. So 7 meters or 7 seconds times 15 meters per second. That gives us 105 meters. So think about this. If we had just continued on at a constant speed of 15 meters per second, we would have had a displacement of 105 meters. Now the area for the triangle, 1/2 times the base times the height, okay? So Let's put our numbers there. We still have 7 seconds. Our height from 15 to 35 is 20. So if we do the math here, we would see that the additional displacement we have due to the acceleration is another 70 meters. So our total displacement here is 175 meters, right? We had to add the 105 and the 70 together to get 175 meters. Now, could we have done this using our other motion equations? Sure. If we could have calculated our displacement, let's see if I can get my pen going here. We could have calculated our displacement using our equation for just that, displacement, right? X is 0 plus velocity times time plus 1/2 AT squared, right? Well, this is 0. Here our initial velocity was 15 times the 7 seconds plus 1/2. Our acceleration here was what, 20 divided by 7. Let's do that real quick. It's about 2.86. And our time squared is 7, right? So if we calculated all that, we should come very close to our value here of 175 meters. Okay, so 2 ways. We can still use our formulas, but if we have the graph, we can calculate the area under the curve. Here's another way to think about it, right? Is the rectangular portion is based on the distance we'd travel if we had constant velocity. And the triangular portion is the incremental distance due to the acceleration. All right, so that's it. We now know what these 3 graphs look like. We know that the slope of a distance time graph is speed. The slope of a velocity time graph is acceleration. And I think I have this last one, but the area under a velocity time graph gives us displacement.